So actually last week we had discussed about power factor a little bit, but we will review it again before going to the next section of the steady state power analysis. So when we have a current, of course AC current flowing through a load having an impedance ZL, then there will be a voltage across that impedance, that load impedance, Vm, or with having a phase angle of theta V. Then there will be power being dissipated there. So depending on the impedance, whether it is inductive or resistive or capacitive, or maybe also combination of that, resistive and inductive, then the voltage will have leading phase or lagging phase towards the flowing current. So here, then if we express the voltage to have leading a phase angle of theta V and the current have a phase angle of theta I, then from Ohm's law, we know that then the voltage across the load impedance ZL will be equals to V equals to ZI. So the phase angle of the voltage across this load impedance will be equals to the phase angle of the impedance plus the phase angles of the current I. Okay, so from phasor multiplication operation, okay, the theta V equals to theta Z plus theta I. So this will be the theta Z. Whether the V leads current or V lags current depends on the phase angle of the impedance. Hence, it will depend on whether the impedance is resistive or inductive or capacitive. If it were pure resistive, then theta Z will be equal to 0. Therefore, then theta V will be equal to theta I. If it is inductive, then as we know from Ohm's law, then if it is inductive, then V will be equals to I M with theta I, then J omega L, right? And J omega L is basically I M theta I, the value L with the phase angle of 90 degrees, 90 degree, if it is inductive. Therefore, then the voltage will have a 90 degree leading phase compared to the current. And vice versa, with capacitive, if it is capacitive, then the V will be equal to Im, phase angle of theta I, then multiplied by 1 over J omega C, right? The impedance of capacities of, or this, if we re-express the impedance in the capacitive, it will be 1 over C, the magnitude, with a phase angle of 90 degree, omega C. This is omega C, this is omega L. So 1 over omega C, and with the phase angle of minus 90 degree. So it means in capacitive impedance load, the voltage will have a lagging phase of 90 degree compared to the current. So usually in this case, then we take x-axis as the voltage. If the current leads the voltage, it means the theta Z is negative. Theta Z is negative. So current leads the voltage here from and therefore the theta Z will be a negative value between minus 90 degree or to 0 degree. And if it is inductive, the voltage will lead the current. So the theta Z will be positive, or between 0 to 90 degrees. And the power, therefore, the instantaneous power will be equals to 1/2 times Vm times Im cosine theta V minus theta I, and this equals to the theta Z. and this is equals to Vrms times Irms cosine this theta z. The apparent power will be equals to the Vrms times the Irms. The power factor is then defined as this power divided by the apparent power. So from here we obtain that it equals to cosine theta v minus theta I, or the cosine theta z. So P, the power, instantaneous power equals to the apparent power times the power factor. If the power factor is 1, where in that case the load is completely resistive, then we will have a power that is equal to the apparent power. So in pure capacitive, here the power factor will be 0 because it has when in pure capacitive impedance, then the current leads by 90 degree, or the voltage lags by 90 degree to the current, and we know that cosine minus 90 degree is equal to 0, and therefore then the power will be equals to, the power factor here equals to 0, the power will be equals to 0. And if it is leading or capacitive, this one, then if it is lagging or inductive, when the current is lagging to the voltage, then the theta z is between 0 and 90 degrees, and we have a power which is also, that it is completely pure inductive, it is also 0, cosine 90 degrees. Let's have an example here. Find the power supplied by the power company. When we have here voltage source, and the transmission resistance is 0.08 ohm, and the voltage across the load is 480 volt RMS. Determine how it changes if the power is changed to 0.9. So here the current is lagging by a power factor of 0.707. Okay, so it is inductive. Cosine theta z here is 0.707, or sorry, it is capacitive. Theta z is negative, 45 degrees. Okay, because it is lagging, it means the voltage is lagging from the current IRMS. The power of the load is 88 kilowatt, and this power equals to Vrms times IRMS times this power factor. So the IRMS will be equals to this 88 kilowatt, 88 times 10 to the power of 3. Be careful with the unit here, since kilo. We multiply with 10 to the power of 3 divided by 480 volt RMS divided by the power factor to obtain the current RMS. From here we obtain 259.3 ampere RMS. The P losses, the loss power, will be equals to I square RMS times the resistance here. Power losses here is the loss of power during the transmission, at the transmission line. So I square RMS multiplied to the resistance value, and this one of the transmission line. So 259.3 squared times 0.08 ohm, and the power loss is 5.378 kilowatt. Then the power at the power company, the power supplied is the power loss here plus the power at the loading. So 88,000 watt plus 5.37 kilowatt. Okay, and we obtain 93.378 kilowatt. What if now the power factor is changed to 0.9? Yeah, if it is changed to 0.9, it means that we will have a smaller current. Flowing through the transmission line, 203.7 ampere RMS. The loss of power then I square times the resistance value of the transmission line, and we obtain 3.32 kilowatt. The losses can be reduced from 5.378 kilowatt to become only 3.32 kilowatt. So if we would like to have small losses, it is important that the power factor is made to be near 1. Okay, so then we can minimize the power loss at the transmission line. Okay, sorry. So from here, the current lags the voltage. Okay, so like this. So the voltage of the source will be equal to 0.08 times the current IRMS plus the voltage here. So voltage here, so equals then 0.08 times 259.3 at this one with the phase angle of IRMS minus 45 degrees plus 480 of the load voltage load. Then the source voltage equals to this one. We change into complex format to plus 480, and we obtain 494.7 minus J 14.7, and we obtain in phasor format it is 495 with a phase angle of minus 1.7 volt. If the power factor is 0.9, so then we multiply 0.08 with this smaller current, 203.7, with the phase angle of minus 35.8. This is with from the 0.9. So we obtain this. This is the theta z obtained from the arc cosine of 0.9. So the voltage source is then 14.47 minus T 7.09. So this is the loss here, the loss here, and then plus 480. This is the loss as calculated from 0.08 times the IRMS. Then we obtain 494 with a phase angle of minus 0.82 degree at the voltage source. Okay, so now let's have another example when the load power is 100 kilowatt and the load voltage is 480 volt RMS with a power factor of 0.707, and we have the transmission line resistance only about 0.1 ohm. Determine the power savings if the power factor can be increased to 0.94. So here we need to calculate the IRMS first and then calculate the power loss at the line, the transmission line, having this resistance of 0.1 ohm when the power factor is 0.707. Then we calculate the IRMS if the power factor is increased to 0.94, and then we calculate the power loss with that new IRMS at the transmission line. After we have the two power losses, then we subtract to obtain the difference between the power factor between the power loss when the power factor is 0.707 and the power loss when the power factor is 0.94. Then we will obtain the power saving. Okay, so the power equals to VRMS times IRMS times power factor. So first we calculate IRMS. It's 100 kilowatt divided by the VRMS 480 volt divided by power factor, and the power loss at the line, transmission line, we calculate from this IRMS squared times the R line, or this is we substitute using this value equals to the power square times R line divided by VRMS square to obtain the and then divided by 1 over square of power factor. And when the power factor is 0.707, the power loss is 100 kilowatt or 10 to the power of 5 squared, so equals to 10 to the power of 10, multiplied by 0.1 ohm divided by 480 volt of the load voltage, RMS, divided by 1 over 0.707 squared. And we obtain here 2 times 4.34 kilowatt. This is the loss of the power at the transmission line. When the power factor is increased to 0.94, we calculate again the loss of the power loss at the transmission line. So now it will be smaller, only 1.13 times 1.34 kilowatt. The saved power will be 2 minus 1.13 times 4.34 kilowatt, or 0.87 times 4.34 kilowatt, so equals to 3.77 kilowatt. Yeah. So quite significant saving. So here, the more we can, for example, here, if it is 0.707, so around this value, we will have a loss of 8.68, so around this region. When we increase the power factor to 0.94, so the power loss is only 3.77. This one, 1.13.434 kilowatt, so around somewhere here, 4 point something kilowatt. So here we see how significant the power saving is. So let's draw. So when the power factor is 0.707, then we have, or this one, this value. So the value is about here. This is 8.68 kilowatt. So when the power factor is 0.94, or around this value, then we have the loss is around 4 point something kilowatt, almost 5. So here the save power is 3.77 kilowatt. Okay. So this is the benefit to have when we can have increase power factor as nearby to 1 as possible to save power. Okay, now let's move on to the next concept in this steady state power analysis, which is the concept of complex power. Okay, the concept of complex power. The complex power here is defined as S equals to VRMS multiplied by the conjugate of the IRMS. So in real power, for example, we have here P equals to VRMS times IRMS times the power factor. In complex power, it is VRMS times the conjugate of IRMS. So again, is we have a load represented by this impedance Z with a phase angle theta Z, and the voltage across it is VRMS, and a current of IRMS flows through that impedance load. Then the complex power equals to VRMS with the phase angle of theta V multiplied by the conjugate of the IRMS. So IRMS with the phase angle of theta I conjugate. So this equals to basically IRMS with a phase angle of minus theta I. Okay. So the conjugate of IRMS will be equals to IRMS. The magnitude is still the same, IRMS, but then the phase angle will be the negative of the original phase angle. This conjugate in complex analysis. Then it means the S will be equal to VRMS times the magnitude IRMS, having now the phase angle will be theta V minus theta I. Okay. So S, and since this is a complex, when we transform into complex notation, this is from this phasor format, this becomes VRMS times RMS, the magnitude, the real component will be VRMS times ERMS times cosine of this angle, theta V minus theta I. Then plus the imaginary part, or J times VRMS IRMS sine theta V minus theta I. So this is the active power. The real part is the active power, while the imaginary part becomes the reactive power, Q. The active power P and the reactive power Q. This is there is a phase difference between the voltage and the current. The unit of apparent power here, VRMS IRMS cosine theta V minus theta I, or theta Z, are volt ampere. Similarly here, this is also volt ampere. So the magnitude of S will be equals to VRMS times RMS. Or here, this is equal to the power times the power factor. Yeah. Cosine, the power factor is this one, cosine theta V minus theta I. So if we draw on phasor diagram, if yes, we have here VRMS having a leading phase angle of theta V minus theta I here. Maybe this is the IRMS. Then the active power is in phase with the voltage RMS. Yeah, this is because it is the VRMS multiplied to IRMS cosine theta V minus theta I. If this is IRMS, RMS cosine theta V minus theta I is the component of IRMS, which is in line with the voltage RMS. The reactive power, on the other hand, comes from voltage IRMS multiplied to IRMS sine theta V minus theta I. From trigonometry, we know that the IRMS sine theta V minus theta I will be the current, the component of the IRMS, which is perpendicular to the VRMS. And that makes the reactive power. So here, if we know if current is leading the voltage, okay, then the IRMS will be in this direction. So the reactive power will be in this direction. That will be in the case of capacitive, when it is capacitive circuit. So when theta V minus theta I is positive, it means that the voltage is leading the current. We will have an inductive power, because then the reactive power Q is positive. But when voltage is lagging the current, so theta V minus theta I is negative, then we will have minus Q, capacitive. So because then the sin theta V minus theta I is negative. The imaginary value will be negative. Okay, another usual form here is that voltage RMS equals to Z multiplied by IRMS. Then the voltage, the complex power here, S will be equals to Z multiplied this voltage, from this definition, voltage RMS, which comes from this Ohm's law, Z impedance times the IRMS, that multiplied to the conjugate of the IRMS, multiplied to IRMS. Then this will be equal to Z multiplied by IRMS multiplied to the conjugate of IRMS will be equal to the magnitude of IRMS squared. Okay, because then the imaginary part will cancel each other. From here, then, since the Z is equal to R plus the resistance value plus the J reactance X, okay, so the active power P will be equal to, from here, the R, the value of the real part of the impedance, which is resistance, times the the magnitude of IRMS squared. Then the reactive power will be Q will be equals to the reactance part of the impedance X multiplied to the IRMS squared. Okay, so if we draw in phasor diagram, the P reactive, the active power will be this one in the real part, equals to the I square times the real of impedance, or basically the resistance. And the S, the complex power, the reactance here, the reactive power Q, is the imaginary part, will be equals to the I square RMS multiplied to the imaginary part of the impedance, which is basically the reactance X, X times the R square RMS. Then the complex power equals to this P plus JQ, P plus JQ, or I square RMS. R plus J I square RMS X. This one indicated by this factor, this arrow. So the operation is similar to factor operation. For a resistor, the theta V minus theta I, the phase angle difference between the voltage and the current is equal to 0. And that is why the cosine of this difference, theta V minus theta I, equals to 1. So what we will have is only active power. The reactive power will be equals to 0. Yeah, since theta V minus theta I equals to 0, this equals to VRMS times IRMS, while this equals to 0. Sine 0 equals to 0. The reactive power is 0. For inductor, on the other hand, theta, for pure inductive system, theta V minus theta I equals to 90 degrees. Yeah, theta, the voltage leads the current by 90 degrees. Then the active power VRMS will be equal to VRMS IRMS cosine 90 degree, or which is basically cosine 90 degree is 0. So it doesn't have any active power. The reactive power, on the other hand, is due to the inductive reactance. Yeah, it equals to VRMS times IRMS sine 90 degree, and sine 90 degree equals to 1. That's why it will be equals to VRMS times IRMS. And the reactive power is larger than 0. When the case is pure capacitor, theta V minus theta I equals to minus 90 degrees, because the current leads the voltage by 90 degrees by J omega, or J, the phase is J, or the voltage lags the current by 90 degrees. So in this case, then, similar to inductor, the active power will be equal to 0, because cosine minus 90 degrees is 0, while the reactive power will be equals to sine negative 90 degrees, or negative 1 times the VRMS times IRMS. So the reactive power will be less than 0 or negative. And we know if the reactive power is less than negative 0, it means that it supplies, it's not absorbing reactive power, but instead it is supplying reactive power. Okay, what if we have a problem, then how to solve it to determine the active power and the complex power S. So if Vt, the function of voltage is a function of time, and current is a function of time, are known, and we wish to find the active power P when we know the impedance Z with the phase angle theta equals to R plus Jx, there are two approaches. The first one, step 1, is we determine the V and current, the voltage and the current maximum, and then calculating the active power to be VRMS times IRMS cosine theta, or theta Z, theta Z here from the impedance, or V equals to VRMS times the RMS cosine, and theta V minus theta I, because voltage equals to I times Z. Okay, and that's why that Z will be equals to V divided by I, or theta Z here equals to theta V minus theta I. Then, to determine the power also, we can use the current here, IT, to calculate the real part of the complex power. And then the P, the real part of complex power, is basically the active power. So active power is the real part of the complex power, equals to I squared times the real part of the impedance, which is the resistance, like I squared times R. So from here we know that the power is not equal to V squared divided by R, as we may have learned in semester 1 for pure resistive network. This is not true, especially when the reactance is not equal to 0. Let's try to solve some example here. Here, for example, we have a load having a power of active power of 20 kilowatt. So the power factor is 0.8, yeah, lagging. So it means it is an inductive. The power, the current is here. IL is lagging to the power, to the voltage, with the power factor of 0.8. The voltage at the load is 220 volt with a phase angle of 0 RMS. The impedance here ZL equals to 0.09 plus J 0.3 ohm. And then the frequency is 60 Hertz. This is common frequency for power line. And we have here the transmission line having an impedance of 0.09 ohm plus J 0.3 ohm. You are asked to determine the voltage and power factor here at the input to the line. So you are asked to determine Vs here and its power factor. So let's draw here that the power is the active power here. The 20 kilowatt will be in the real axis, and the complex power here, if either it is inductive or capacitive, it is inductive, then you have positive reactive power plus Q, and since theta V will lead theta I, and actually this is the case here. When the circuit is capacitive, then we have negative reactive power minus Q, because then theta V will be lagging from theta I, or theta V minus theta I will be negative angle. So the power here, the indicated power 20 kilowatt, is equals to the real part of the complex power. Okay. So this will be equals to the magnitude of S cosine theta V minus theta I, or this equals to the power factor, right? The magnitude of the complex power times the power factor. This is cannot be seen. We look, this is the slide. Picture can be displayed. Q square equals to SL square minus P square. This is the inductive. This is the complex power itself minus P square. So to obtain, so since like this, yeah, this is basically this using Pythagoras theorem, then we can obtain the Q, the magnitude of Q, S square minus the P square, and this is inductive. That's why we put L. So the Q here equals to 15 kilovolt ampere. The reactive power equals to 15 kilovolt ampere. Okay, and the SL here equals to 20. The SL equals to 20 plus J 15 kilovolt ampere. And or in phasor format, it equals to 25 with a phasor angle of 36.87 degrees. The SL will be equals to the complex power, will be equal here, equals to the VL, voltage at the load, here 220 0 degree RMS, multiplied by the conjugate of IL here. And IL will be equals to the conjugate then of SL divided by VL. So SL here is 25,000 here, 25 kilowatt, with the phase angle 36.87 degree divided by 220 volt. with a 0 degree phase angle. So this equals to this magnitude divided by 220, 25,000 divided by 220, we obtain 113.64, and this minus 0 is 36.87. Then since it is conjugate, it is the negative of this angle, so become 36 minus 36.86. So the current, this is the IL. Then IL can be obtained here from 20,000 kilowatt here power plus J 15,000. This is divided by 220. So this is in complex format, in complex format. So this equals to 90. So basically this is 90, the same as this one here, 90.91 minus J 68.18 ampere. So this is expressed in complex format, while this is expressed in phasor format. Then the voltage at the source, voltage source, will be equals to this one, the transmission line impedance 0.09 plus J 0.3 ohm times the IL here, plus the voltage at the load, which is 220 phase angle of 0. So this multiplied by this value, this impedance of the transmission line multiplied to the current IL plus 220 volt. So from here we obtain 248.63 ampere, volt plus J 21.14 volt, or in phasor format equals to 249.53 with a phase angle of 4.86 degree volt. So this is the voltage. Okay. Then this is the VS, with a phase angle of 4.86. Yeah, now the question is, second question is that determine the power factor at the input to the line. The IL is the same here because the IL flows through all the part of the circuit here in the components of the circuit in series. And IL is this one, 113.64 with a phase angle of negative 36.86, and the power factor will be cosine theta V minus theta I. So to cosine 4.86 minus 36.86, or cosine 41.72 degree equals to 0.746 lagging. So it means that the current lags the voltage. Okay. Now compute another example. Compute the average power flow between these two networks. So determine which one is the source of the power. So it means if the source of the power, then the other part will be absorbing power or dissipating power, positive, according to the passive sign convention, while the source should be negative. So here in the network A, the voltage at A equals to 120 volt RMS with phase angle 30 degrees. Voltage at B is 120 volt RMS with phase angle of 0 degree. Then a current flows to the transmission line between the two networks, and the impedance of the transmission line here is J1 ohm. Here. Okay, so the current equals to VA minus VB divided by the Z, 120 with phase angle 30 degree minus 120 with phase angle 0 degree divided by J1 ohm. So here we have to convert into complex format. So it becomes like this, 103.92 plus J60 minus 120 divided by J. So the current equals to 60. So since this becomes the complex, becomes the real part now, 60 plus 103 minus 120 is minus 16.08. Then divided by J becomes, and then you multiply by J over J, it becomes J plus 16.08 ampere RMS. Okay. So in phasor format, this equals to 62.12 with a phase angle of 15 degrees ampere RMS. So based on the passive sign convention, the SA, the complex power at A, will be equals to the VA multiplied by the conjugate of the IRMS. 120 with phase angle 30 degrees multiplied to 62.12 phase angle of minus 195. So since this one is 15 degree, then the supposed to be minus 15. This one minus 195 degree. The conjugate of this. So this equals to 7.454 with a phase angle of minus 195 degree. So since the value here is by passive sign convention, it means that the network A receive power because it is in negative. The power at A here 7,454 cosine 165 degree. Cosine 165 degree is negative value, minus 7,200 watt. Okay, then the power at B, we calculate now the complex power at the network B equals to the voltage B times the conjugate of the IRMS, 120 volt at phase angle 0 degree times the 62 point. Oh yeah, now I understand. So this is minus M minus I conjugate, not I conjugate, because the current here is leaving network A. If it is leaving network A from the positive terminal, and we know from passive sign convention that we have to apply negative sign. Okay, so this equals to negative 62.12 phase angle of minus 15 degree, minus 15 degree. Or if we re-express in 62.12 in with phase angle of minus 195 degree. Okay. So if we draw, for example, this one, current I equals to this value, right? So if we draw in the phase, this will be like this, 62.12, and the phase angle is 15 degree. Then, since it is minus I here, then it becomes and conjugate, and conjugate. Minus I only will be this one. This is I. This is minus I. Okay. Then minus I conjugate, you reflect towards the x-axis. So this becomes this. This is minus I conjugate. Okay. So the magnitude is still 62.12 ampere, but now the angle will be, you can express as this angle. This is be 15 degrees. It means then it is 180 degrees minus 15 degree equals to 165 degree. Or you can express as negative 195 degree. If negative, then from here to this. This is negative 195 degree. Okay, either way, you will obtain this value later. 7 point this times this 30 degree. If you use 165 degree, then it becomes 30 plus 165 degree, or equals to 195 degree. 195 degree, and the cosine of 195 degree is also negative value. So you will obtain still, this one. You will obtain minus 7,200 watt. Since it is negative, then power is being absorbed by A. Okay, is it clear for everyone? Then the power at B is 120 volt times the IRMS conjugate. IRMS conjugate is this one, 62.112, this one, yeah, minus 15 degrees. So the value is then 7,454 with the phase angle of minus 15 degrees volt ampere RMS. The power at B will be equals to 7,454 cosine minus 15 degree or equal to 7,200 watt. So A, network A is receiving power and network B is supplying power. Okay. Oh, sorry, the other way around. Power B, A is supplying power, B is absorbing power. Yeah. So because according to power sign convention, if the power is positive, means it is absorbing power, dissipating power. When the sign is negative, it means it is supplying power to the other network. Okay, so let's have a break for a while. Yeah, and we will continue with the next